This video is about the reaction mechanism that involves carbon-carbon multiple bonds. When I say carbon-carbon multiple bonds, it includes alkenes, alkynes, and even aromatic ring. In this video, we are going to focus more on alkene and aromatic system. We are not going to discuss alkynes because the number of reactions with alkynes is very less. First, let us go for alkene. We have three types of alkenes. The first one, isolated alkene. The double bond is not attached with any electron withdrawing group or any heteroatom. After this, there will be carbon only. The second one, alkene, that is attached with heteroatom like this, maybe even N or 2. The atom, whatever I have attached here, will have lone pair and it will involve in resonance. As a result, what I get is this resonance structure. Such resonance is not possible in the isolated system. The third type of olefin is olefin with electron withdrawing group. Carbonyl group is the electron withdrawing group. Because of resonance, we get another resonance structure like this. This bond comes like this. I get this resonance structure. This is the alpha carbon, this one beta. Similarly, alpha and beta. Here, the isolated alkene acts as nucleophile. When I go for vinyl ether, this is nucleophile and it is stronger nucleophile. Compared to isolated alkene, this is stronger nucleophile because the electron donating group increases the electron density in the olefin. When I go for the other one, it is not nucleophile, it is electrophile. Because of resonance, I get plus charge on the beta carbon. So first it has to be attacked by some nucleophile. After that, whatever I get is enol or enolate. The enolate may attack another electrophile. If you consider only this system, this particular carbon is electrophile. Now, let us go for alkene, the isolated alkene. To this, if I add electrophile, let us take H plus for example. This double bond will be added to H plus to make a bond with hydrogen. When this bond is added to hydrogen, what we get is plus charge on the other carbon. This bond is common for this CH2 as well as this CH2. When this bond is used to make bond with hydrogen, the valency for this carbon becomes only 3. So there should be plus charge on this carbon. Since I have taken symmetrical alkene, there is no question about the regioselectivity. Even if I go for cyclohexane, one side hydrogen will be added, the other side plus charge will be generated. Even if I add hydrogen this side, whatever I get will be same because it is symmetrical alkene. Suppose if I go for unsymmetrical alkene like this. Now the question is whether H plus will be added to this carbon or this carbon. If I add hydrogen to this carbon, whatever I get is this benzyl cation. This double bond has attacked H plus, so I get plus charge. Suppose if this carbon attacks H plus, what I get is H plus will be added here. Now, which one will be more favor? First one or second? The first one is more favored compared to the second one. The reason it is very clear. In this case, I have got benzyl cation or secondary carbocation. The second one, I have got primary carbocation. Secondary carbocation is more stable compared to primary carbocation. So this will be more favored. Further, this will be attacked by nucleophile. This is given by Markovnikov rule. As rule, H plus is added to the carbon with less number of substituent, and the negative part is added to the carbon with more number of substituent. That is Markovnikov rule. Instead of memorizing, try to understand, try to find out the intermediate that will be formed in the alkene addition. Now let us go for a diene like this. Here I have two types of carbons. This and this, they are identical. Similarly, these two are identical. When I add electrophile, let us take H plus. Whether the H plus will be added to this carbon or the other carbon. Let us go for both the possibilities. In this carbon has added to H plus. There is another possibility, that is this one. Which one is more preferred? Both are secondary carbocation, but this one allyl carbocation. This is not allyl. Allyl carbocation is more stable compared to normal secondary carbocation. So this should be more favored. Further, there may be resonance. Because of that, I can get plus charge on this carbon also. Now the question is whether the nucleophile will be added to this carbon or this carbon. When you go for low temperature, this resonance will be stopped. The resonance will not be that much fast. So when you carry out the reaction at low temperature, the nucleophile will be added to this carbon. If you go for high temperature, this bond will migrate fastly. Because of that, we will get this carbocation also, and the nucleophile will attack here. So this is referred as thermodynamic product, that is more stable product. This one is kinetic product. So at low temperature, we get addition to 1,2 carbon. When we go for high temperature, we get 1,4 addition. Second one, let's go for alkene with electron donating group. If I add some electrophile like Br plus, the Br plus will be added to the beta carbon, because due to resonance I get minus charge on this carbon. So the electron density is more on this carbon compared to this. So what I get is this intermediate. Further, if you add any other nucleophile like methanol, the methanol will attack here. We will end up with this product. Basically, it is bromo-alkoxylation. I have added bromine and OR across the double bond. But the regius selectivity is controlled by the electron donating group. Similarly, you can try to add HBr also. H plus, Br minus. H plus will be added to this carbon, Br minus will be added to the other carbon. Let us go for this particular substrate, dihydropyrene. To this, if you add H plus and alcohol, this double bond will attack H plus from this carbon. After that, alcohol will attack here. We get this one. So basically, it is tetrahydropyrene protection of alcohol. Let us go for alpha beta unsaturated system also. Here there is del plus on the beta carbon. So the double bond will not act as nucleophile. At the same time, if you add some nucleophile, then this will attack. As a result, what we get is this one. Now this can be compared with the enolate, whatever we get in aldol reaction. If you abstract the alpha hydrogen, we get the enolate. When it comes back, it can take some electrophile. What we get is this product. If you quench with H plus or water, we get this one. This reaction is referred as Michael addition. Here let us discuss the aromatic system also. The case of benzene, I have 3 double bonds. So when I add H plus, the double bond will attack this. I get this intermediate. This carbocation may be attacked by Br minus to give this. So basically it is addition reaction, similar to the earlier one, whatever we have discussed in Markovnikov addition. But in this case, the carbocation is not attacked by Br minus. Instead of that, it prefers to undergo elimination to give the starting material back. The reason, aromaticity. The molecule will not prefer to lose its aromaticity. This compound is aromatic, this one is non-aromatic. There is no extended conjugation. Because of that, this is non-aromatic. The molecule will not prefer to become non-aromatic, so it will not be attacked by Br plus, Br minus, it will not undergo addition reaction. Instead of H plus, suppose if I add Br plus, this double bond will attack Br plus. What I get is plus charge on this carbon. In the earlier case, I had only 2 hydrogens, but here I have 1 hydrogen and 1 Br. Which one will undergo elimination? Hydrogen will undergo elimination. As a result, we get the product, bromobenzene. Not only Br plus, we can go for CH3, CO plus, NO2 plus, SO3H plus, and even CH3 plus. So it is possible to carry out the same reaction and the same mechanism for this many electrophiles. These reactions are referred as aromatic electrophilic substitution. Now let us go for aromatic system with OMe, similar to methyl vinyl ether. Here there will be resonance. Because of that, the ortho carbon, in the earlier case it was beta carbon, now also it is beta. This is alpha, this is beta. But in aromatic system, we are not using the term alpha beta. We use ortho meta para. So this carbon is ortho carbon, it gets the minus charge. We get like this. Further, because of resonance, we may get this resonance structure. So there is more minus charge on ortho carbon and para carbon. Further, if I move, this carbon will be ortho carbon. This and this are equivalent. So when we add some electrophile, the electrophile may be attacked by this minus charge or this minus charge. We don't get minus charge on metacarbon. Because of that, the product, whatever we get, will be like this. Here already we have one hydrogen. Finally, the hydrogen will fall back. We get this product. Similarly, here this minus charge will attack the electrophile. There is one more hydrogen. We get this. This hydrogen will be removed. We get para substituted product. So it is possible to get both ortho and para substituted product. It is because of OMe. So OMe is referred as ortho and para directing group. If there is no OMe, we won't get this selectivity. All the 6 carbons will be equivalent. But when we introduce OMe, we get ortho meta para carbons. In that, only ortho and para carbons are more electron rich. They attack the electrophile. So we get the corresponding product. Not only OMe, even OH, OCOCH3, NH2, NHCOCH3, SH and halogen. In all this case, if you see, we have heteroatom which has lone pair. These atoms are attached to the aromatic ring. So they increase the electron density. Because of that, we get ortho and para product. On the other hand, if I go for electron withdrawing group like ketone, this particular part can be compared with the earlier system, whatever we have taken, that is methyl vinyl ketone. Because of resonance, we got this structure. The same structure is possible here also. This bond goes like this, O minus here, we get this. Further, I can move this I get plus charge on this carbon. Now we have plus charge on ortho carbon and para carbon. In the earlier case, we had minus charge on ortho and para carbon. Now if I add electrophile to this particular carbon cannot attack electrophile because it carries plus charge. Similarly, the para carbon also cannot attack the electrophile. So we will not get ortho and para substitute product. At the same time, we have not increased or decreased the electron density on the metacarbon. When we introduce some group, it increase or decrease the electron density only on the ortho and para carbon, not metacarbon. This metacarbon is electron rich. So that will attack. We get this intermediate. After that, it will eliminate. We get meta substituted product. We got this because of the keto group. So keto is referred as meta directing group. Not only ketone, we have all carbonyl groups, maybe aldehyde, ketone, ester, acid, amide, also nitro, nitride. All these electron withdrawing groups are referred as meta-directing group. If you notice, there will be double bond that will be in conjugation with the aromatic ring. We have aromatic ring, after that a single bond, then there will be double bond. In all these cases you can find like that. In nitrile it is not double bond. Here, instead of that we have triple bond. We have two important reactions. Consider the reaction between this ketone and aldehyde. We have three different types of alpha hydrogen and two different types of carbonyl group. So the number of products whatever we get will be 6 products. In the presence of base we get 6 aldol products. Is there any possibility to get only one product? It is possible. If you go for triethylamine and TMS chloride, we get enol ether. For the time being, I don't bother the stereochemistry. It may be E or Z. To this, if I add this aldehyde, this double bond will attack here. Which carbon? That is controlled by this oxygen. The oxygen lone pair will go like this. There is more minus charge on this carbon. So this carbon will attack here. We get only one product. This will be the product. It is known as Mukayama aldol reaction. Generally, it is carried out in the presence of titanium tetrachloride. The reason, the alkene is not that much nucleophilic. So, we increase the electrophilicity of this carbonyl carbon by adding Lewis acid. This lone pair will coordinate with titanium tetrachloride. As a result, the del plus on this carbon is increasing. That is attacked by this silyl enol ether. We have one more reaction which is not that much popular. When we add alkene to formaldehyde, the alkene cannot attack this carbonyl carbon because the del plus is very less. At the same time, if I add H plus to this, the del plus on this carbon will increase. I can go even for the resonance structure. This will be the other resonance structure. So the double bond will attack this. Which carbon will attack? This carbon or the other one? This carbon will attack because when it is attacked, I will get secondary carbocation. So what I get is like this. CH2OH. Further, it can be attacked by nucleophile. That is one possibility. If you have done the reaction in water, you will get OH here. Or it may undergo elimination. This hydrogen or this hydrogen will go like this. We will get allyl alcohol. So basically, it is known as Prince reaction. In addition to that, we have few more options and we may get few more products. That's why generally Prince reaction is not asked in CSR exam because the selectivity is very poor. The last one, Diels-Alder reaction. Even though it is a concerted mechanism, The reduced selectivity can be explained based on electron richness. When I go for some electron donating group on this carbon, the lone pair will go inside. Because of that, the del minus is more here. I go for the resonance structure itself. So there is del minus here. It will be like this. Now, if I add acrylate, because of resonance, there is del plus on this carbon. Already we have seen that. So this minus and this plus will be added. So the product, whatever we get, will be like this. There is another possibility, that is, I turn this, I add like the other way, and if you place like this, you get this product. This one is not at all favored. Only this product will be formed. The reason, we have more del minus on this carbon, that is added to the carbon which has more del plus. Generally, the selectivity has to be explained based on orbital coefficient. But it involves quantum chemistry and it will be very difficult to understand. So that's why we go for the concept of electron richness. Suppose if I introduce electron donating group on this carbon, once again I go for resonance structure, I get minus charge on this carbon, the other double bond is not affected, I get this. To this, if I add acrylate, we have plus charge on this carbon because of resonance. This minus charge will attack here, goes like this. So the product, whatever we get, will be like this. So here the two substituents are on 1,4 carbon atom. The earlier case, they were on 1,2 carbon atoms. So the products, whatever we get, will be either 1,2 or 1,4. 1,3 will not be preferred. Suppose in this case, if I place the acrylate like this, I may end up with this one. Here the two substituents are on 1,3 carbon atoms. This is not formed. This is not favored. The reason, the electron richness on this carbon is very high. Similarly, the electron richness is more on this carbon. They will not combine. Since the electron richness is more, it will look for the carbon which has less electron density. So that is this one. Let us go for ketene. I go for the very popular dichloroketene. To this, if I add a carbon like this, what will be the product? Whether I will get this one or the reverse. Like this. It is observed this one is more favored. What is the reason? In the ketene, this particular carbon carries del plus. Here, this carbon acts as nucleophile because when it attacks, I get plus charge. So the intermediate, whatever I get, will be benzyl cation and minus charge here. This minus charge is stabilized. Similarly, this carbocation is benzylic carbocation, it is more stable. So this intermediate is more favored they will combine to give this product. If I go for the other way, I will get carbocation on this carbon which is not stable. So I can explain the selectivity, reduced selectivity in ketene addition based on this. You have to remember, it is concerted mechanism. But still, the reduced selectivity can be explained based on this.